All right, today we're jumping into a real head-scratcher from the world of physics, the predictable decay of an unstable atom. I mean, how can something be perfectly random and perfectly predictable at the exact same time? It just sounds impossible, doesn't it? But that's the central puzzle of radioactive decay. And believe it or not, we're going to unravel this whole thing. And it all starts with a single, kind of unhappy atom.
Yeah, unhappy, or more scientifically, unstable. And to really get what that means, we need to zoom all the way in, right to the very heart of the atom, the nucleus.
Okay, so picture the nucleus like this tiny, super-packed little team. For that team to work, to be stable, you need just the right balance of players, your protons and neutrons. In smaller atoms, it's pretty simple, usually a 1-to-1 ratio. But as those atoms get bigger and bigger, you start needing more neutrons to kind of act as glue to keep all those positively charged protons from flying apart.
And here's a perfect example of that balancing act. Look at carbon-12 on the left. 6 protons, 6 neutrons. It's totally balanced, totally stable. It's happy, it's not going anywhere. But then you've got its cousin, carbon-14. Same 6 protons, but 8 neutrons. See that? It's out of balance. Those 2 extra neutrons make the whole thing unstable. It's just a matter of time before it has to do something about it, before it falls apart.
So, what happens when that unstable nucleus just can't take it anymore and decides to break down? Well, that's what we call radioactive decay. It's basically the atom's way of trying to chill out and get back to a stable, happy state.
Yeah, this is how the atom fixes its own problem. It literally just jettisons parts of itself to get that balance back. And the stuff it throws out, that's what we call radiation. And it turns out there are a few different ways it can do this.
So, one of the main escape routes is called alpha decay. This is what happens when a nucleus is just too heavy, it's overweight. So to slim down, it just spits out a little package. 2 protons and 2 neutrons all bundled together. And boom! By losing that little chunk, the atom literally turns into a brand new, lighter element.
Then you've got beta decay. This is what happens when the problem isn't being too heavy, but having the wrong ratio, too many neutrons. And this is where it gets really cool. In this amazing little quantum trick, one of those extra neutrons suddenly flips and becomes a proton. To keep everything balanced, it spits out a super high-speed electron. The atom's total weight barely changes, but, and this is the key part, because it now has 1 more proton, it's a completely new element. This is literally how our unstable carbon-14 turns into stable nitrogen.
Now, you've probably heard that not all radiation is the same, and that is absolutely true. Think of it like this. Alpha particles are like little bowling balls. They hit hard, but they don't go far. A single piece of paper can stop them cold. Beta particles are a bit zippier, like a fastball. You'll need something like a thin sheet of aluminum to block those. But then there's gamma radiation. That's a whole different beast. It's pure energy and it's super penetrating. You're going to need thick lead or solid concrete to have any hope of stopping it.
Okay, so we get it. Atoms decay. But this brings us right back to that paradox we started with. Let's say you're looking at just one single atom of carbon-14. When is it going to decay? Is it going to be in the next second? Tomorrow? 1,000 years from now? What's the answer?
The answer is nobody knows. And I mean nobody. We have absolutely no way of telling. For a single individual atom, the process is completely 100% random. There's no timer, no warning light, nothing. You just can't predict it. It sounds like total chaos, right? But it's not.
And this is where the solution to the whole paradox lies. We can't predict what one atom will do, but we can be incredibly certain about what a huge group of them will do. One atom is a total mystery. A billion atoms? That's a predictable pattern. It's the magic of statistics. Scientists realized they could find a rock-solid, reliable pattern inside all that randomness.
And that amazing pattern has a name: half-life. This is the key to everything. It's the specific amount of time it takes for exactly half of all the unstable atoms in a sample to decay. We don't know which half, just that half of them will be gone. It's a statistical promise.
All right, let's make this concept of half-life super clear by walking through a real-world example. Okay, so let's say we've got this sample, and its radioactivity, its activity, is at 80 units, or becquerels. And we know its half-life is exactly 2 days. So we start the clock. 2 days go by. That's 1 half-life. And boom, the activity is cut in half, down to 40. Now we wait another 2 days. What happens? It halves again, right down to 20. Another 2 days pass, and you guessed it, it halves again, down to 10. It's like clockwork, perfectly predictable.
But check this out. Here's a really interesting detail. Notice the pattern. 80 becomes 40, then 20, then 10, then 5, then 2.5, and so on. We're always just taking half of whatever is left. So the amount gets smaller and smaller and smaller, but mathematically, it never actually gets to zero. It just gets closer and closer forever.
And once you really get this whole halving idea, you can actually use it to make some seriously accurate predictions.
All right, let's do a little challenge. The half-life of an element called cobalt-60 is 5 years. So if I give you a 100-gram chunk of it right now, how much of that original cobalt-60 will still be there in 15 years? Take a second to think it through.
Ready? The answer is 12.5 grams. If you got that, awesome. If not, no worries at all. Let's break down exactly how we got there.
It's actually a super simple 3-step process. First things first, how many half-lives are we talking about? Well, we've got 15 years, and the half-life is 5 years, so 15 divided by 5 is 3. 3 half-lives. Okay, step 2. What fraction is that? That just means we have it 3 times. So half times a half times a half, that's 1/8. And the final step is just to find 1/8 of our original 100 grams, and that gets you to 12.5 grams. See? Simple, predictable, and really powerful.
And really, that's the whole point of this. The fate of one single atom. Total, complete, random chance. But the fate of a huge collection of atoms, that's governed by half-life, a law of nature. It's just this beautiful idea that lets us pull perfect, reliable predictions out of what looks like total chaos.
So this all leaves us with one last kind of tricky question to chew on. If the radioactivity is always just halving, and it never really disappears completely, how do scientists or governments ever decide when something like nuclear waste, for instance, is officially safe? Where do you draw the line? It's a fascinating spot where the hard rules of physics meet up with human judgment. Something to think about for sure. Thanks for tuning in.